Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on November 30th, 2025, about 3 days ago. This paper shows that a two-stage deterministic model, called Lotus-2, can use powerful diffusion world priors to reach state-of-the-art monocular depth estimation with only 59,000 training samples, which is less than 1% of the data used by some rivals. The paper is titled, Lotus-2, Advancing Geometric Dense Prediction with Powerful Image Generative Model. And as we will see later, the implications for data-efficient 3D understanding are pretty striking. Alright, Figure 1 provides an immediate visual feel for what Lotus-2 actually changes. The left column shows challenging input images, while the middle column with the Lotus-2 baseline tends to blur depth and surface details in vines, paintings, and transparent glass. The right column with Lotus-2 preserves thin structures, clean object boundaries, and crisp surface normals, which means the method recovers more accurate three-dimensional geometry from the same single image. While Figure 2 explains how the traditional stochastic adaptation works and why it struggles with stable geometry, the left side shows the input image and its depth annotation being encoded into latent grids, which are compact numerical representations. The middle region illustrates a noisy latent starting point that gradually moves towards the annotation latent over many steps. The transformer block predicts a velocity field that points from noise to annotation, and the loss box on the right trains this process, but the random noise seed makes the final prediction non-deterministic. So, while Figure 2 highlighted noisy multi-step adaptation, Figure 5 presents the clean single-step core predictor in Lotus-2. The left panels show an input image and its depth annotation being encoded into paired latent grids. The middle block labeled Equation 11 produces a combined latent that directly equals the image latent because time is fixed to 1. On the right, the transformer with the local continuity module predicts the clean annotation latent in a single deterministic pass, and the loss simply measures their squared difference. So while Figure 5 focused on training the core predictor, Figure 10 shows how inference actually runs end-to-end. The input image is encoded into a latent grid, which enters the core predictor transformer with the local continuity module to give a first structurally correct geometry guess. The detail sharpener transformer then iteratively refines this latent using a short rectified flow with at most about 10 noise-free steps. A final decoder converts the refined latent into the dense depth or normal prediction, so the whole pipeline stays fully deterministic, yet still recovers sharp fine details. Alright, Figure 9 backs up the inference story by showing how the detail sharpener is actually trained. The left side contrasts a coarse depth or normal map with its fine annotation, which defines what extra detail the model must learn. Both are encoded into latent grids, then Equation 16 blends them over time to create intermediate latent targets. The transformer learns to predict the velocity from each intermediate latent toward the fine one, and the loss on the right penalizes any mismatch between this predicted velocity and the true difference vector. So, while Figure 9 focused on how refinement is learned, Table 1 reports how well that training pays off across real depth benchmarks. Table 1 lists many competing methods and their training data size, then reports depth errors and accuracy for indoor, outdoor, and varied scenes. Lotus-2 appears near the bottom row, using only 59,000 synthetic samples, yet achieving top or second best scores on most datasets. The rightmost column shows that Lotus-2 attains the best average rank overall, so it outperforms models trained on tens of millions of images. So while Table 1 focused on depth, Table 2 turns to zero-shot surface normal estimation across 4 datasets. The table lists each method, its training data size, and then the mean angular error and 11.25 degree accuracy for indoor, outdoor, and challenging benchmarks. Lotus-2, highlighted in orange, uses only 59,000 samples, yet matches or beats most rivals on several datasets. The rightmost column shows Lotus-2 reaching the second best average rank overall, barely behind Lotus-2, that relies on roughly 150 times more data. Lotus-2 shows that treating diffusion backbones as deterministic world priors with a single-step core predictor plus a constrained refinement stage can deliver state-of-the-art 3D geometry from tiny training sets. This points toward more data-efficient, stable vision systems for robotics, AR, and beyond. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.